Again, let's look at our object as it's going around in the circle, and we'll look at two close by points in the motion. When the object is here, it's going to have some velocity v initial, and then when it's up here, it will have some velocity v final. And then I've redrawn those velocity vectors again over here. So this is v initial and v final. I haven't labeled them yet because we'll see why in just a second. Now, what I'd like to do is think about this triangle with this side, and then I'm going to connect these with a straight line. And then let's connect this triangle here across the tips of the two velocity vectors there. Now I want to compare this triangle with that triangle. First of all, with this triangle, what are the lengths of these two sides? Well, that's just the distance from the center to the object at this point, and the distance from the center to the object at this point. Well, those two sides are both the radius of the circle, r and r. While these, what are the lengths of these two sides? Well, this one is the length of v initial, this one is the length of v final, but we have uniform circular motion with the speed constant. What does that mean? The speed, the magnitude of the velocity is constant. So these two sides have the same length, just the speed of the object. Now, what's this length, the distance between them? Well, it's very close. The straight line distance is not the same as the arc length. So the arc length between the 2 points, the actual distance that the object travels, which is along the arc of the circle, is not quite the same as the distance between the 2 points. We can imagine that if this were going around on a circle, the straight line distance between this point and this point is not the same as the arc distance. However, if we made these 2 points closer together, these look like it's closer to a straight line. If we put them very close together, the arc of the circle looks even closer to being a straight line. Well, remember, we're going to let the time difference between these 2 points go to 0. So we are going to assume that these 2 points get closer and closer and closer together. Well, as they get closer and closer together, the distance between them along the arc is going to be essentially the same as the straight line distance between them. Well, what's the distance along the arc? It's the distance that the mass moves in a time delta t. If the difference between these two points is a time delta t, how far does it move in a time delta t? If it's traveling at a speed v, it's going to go v delta t. So this length here is going to be v delta t. The distance traveled at a speed v for a time delta t. Okay, good. What's this length up here? Well, remember, this is v1 or v initial and this is v final. This was the length that we looked at before. That's the delta v. That is the distance delta v. Okay, great. Well, let's think about what's the angle between these. This is going to be some angle delta theta. The angle that the mass rotates through or revolves through, actually, over the time delta t, some delta theta. Well, how much does vi rotate to vf in that time interval? In other words, from here to here, how much has the initial rotated to final? Well, I think that we can see that if we have this radius here and the velocity vector is perpendicular to that, if we rotate the radial line delta theta, v is also going to rotate delta theta. You can go through this more in-depth trigonometrically, but I think that we can kind of visualize it, that if we rotate the radial line and maintain the velocity vector perpendicular to the radial line is going to rotate through the same angle that the velocity vectors rotate through. So what does that mean? It means that this angle here is also delta theta. So what do we have? We've got a triangle here with 2 equal sides and an angle of delta theta, and a triangle here with 2 equal sides and the same angle between them, delta theta. These 2 triangles are called similar triangles. They're not the same size because one has a side length of the radius of the circle and the other has a side length of the velocity, the speed of the mass, but they are similar. In other words, they have the same shape. same shaped triangles. And for similar triangles, the ratios of the side lengths have to be the same. In other words, the ratio of the short length to the long length, in other words, V delta t over r must be the same as the short length, delta v, over the long length, v. So because they are similar triangles, we must have v delta t over r equal to delta v over v. Well, let's multiply both sides by v, and what do we get? We'll get v squared, and divide by delta t. So we'll get v squared over r equals delta v over delta t. There we go. But delta v over delta t, that is exactly the term that is in the definition of the acceleration if we take the limit that delta t goes to 0. Now, originally we had these as vectors, a vector equals delta v vector, but we've already found the direction of those vectors. We've already found them to be centripetally pointing towards the center. So we can just look at this in terms of the magnitudes, the magnitude of the acceleration and the magnitude of delta v. And what we find is that the magnitude of delta v over delta t is v squared over r. For a small time interval, but that's exactly what we want. We want the time interval to go to 0. So what happens as delta t goes to 0? Well, we get exactly this, v squared over r. So what do we find? We find that the acceleration, which we'll write as a sub c, because we know it's a centripetal acceleration, is v squared over r. What does that mean? When an object is going around uniform circular motion, okay, just like we had before. So an object going around in a circle, uniformly constant speed, uniform circular motion. It is accelerating. The acceleration is directed toward the center. So wherever the mass is, when it's over here, it's accelerating this way. When it's up here, it's accelerating that way. When it's here, it's accelerating that way. Always toward the center of the circle. And what's the magnitude of the acceleration? The magnitude is v squared over r. Excellent. If that's the only acceleration, or I should say, if the only force acting on the object is the centripetal force, like the tension in the string, then this will be exactly the acceleration of the object, and we'll have that the net force acting on the object is m times a, and if that's the acceleration of the object, which is centripetal, then we must have a centripetal force, and the centripetal force must be m times the centripetal acceleration, m v squared over r. So what does this mean? That means that in order to keep an object going around in a circle at a uniform speed, there must be a force acting on it towards the center of the motion. The magnitude of that force is equal to mv squared over r. So we can actually see some physical examples of this. mv squared over r. So what does that mean? So if this is going around a circle of radius r with a speed v, the tension in the string has to be mv squared over r. If I make it go faster, if I speed it up, I have to apply more tension. Good grief, I'm going to kill myself. To make it go faster requires a stronger force, a greater tension, and you can definitely feel that if you try spinning this around. What if we decrease the radius? So if I have this going around at a large radius at some speed, and then I try spinning it in a smaller radius, but at the same speed, again, it's much harder to do. Decreasing the radius with a constant speed means you must increase the force. Increase the acceleration, increase the force. Very, very good. Let's take a look at some examples of this. Let's imagine that there is a car going around a curve. So the car's on the road curves, the car is going around the curve. This is not going around in a complete circle, but even though that part of the motion is a circle, while the car is going around that part of the circular part of the curve, we can think of it as going around uniform circular motion, assuming it travels around at a constant speed. So something doesn't have to go around a complete circle to be uniform circular motion. If it's going around a part of a circle, it's undergoing uniform circular motion if it's traveling at a constant speed during that part of the motion. So it's going around the curve. We know we're looking at it from above. So if we were to look at it, say, from the side, we've got the car, looks like this here, and it's going around, say, like this, going around the curve this way. We know that there is a normal force acting on it and a weight acting on it this way. Those are acting in the vertical direction, in and out of the board from this direction. But what force is acting on it? What's the centripetal force? What force is acting on the car to make it go around in a circle? In other words, to keep it on the road. What force is acting centripetally? Well, if this has got some radius of curvature for the curve that looks like this, what's the centripetal direction? It would be this way. In other words, sideways, here. What force is acting on the car, making it going to make it curve sideways? Well, let me ask you, if this were a very, very icy road, would the car be able to go around the curve? Well, no. So what's acting on it to keep it on the road? It's friction. It's friction between the tires and the road. It's a type of friction called rolling friction, but we're going to treat it like static friction. We'll just assume it's acting very much like static friction. So static friction is causing the centripetal force keeping it on the road. Well, let's take a look at that. What's the maximum centripetal force that the object could have, that could act on the car? What's the maximum frictional force? What's the maximum static frictional force? It's Fs max. Fs max. So the maximum centripetal force that could act on the car would be Fs max. And what is Fs max? It is mu smg. That's the maximum centripetal force that we could have. Then what is the centripetal force equal to? Remember, it's mv squared over r. So if we equate mu smg with mv squared over r, let me just remove this for the moment. Mu smg equals mv squared over r. Let's see if we can figure out how fast can this car go. What's the maximum speed it can go? Because remember, the faster something is moving, the greater the centripetal force would have to be. The faster this car goes, the greater the centripetal force. In other words, the greater the frictional force. But the frictional force can only increase to a maximum value. So there is a maximum speed that the car can go around the curve and still stay on the road. If it goes too fast, what's going to happen? It will skid off the road. And maybe if you are a driver, you might have noticed that. If you try to go around a curve too fast, the car might start to skid. So what's the maximum speed that we can have? Well, when these are equal to each other, that would be the maximum speed. Multiply by r, divide the m cancels, and what do we get? We get V max equals mu sgr root. There we go. So let's notice a couple things. The faster it goes, the more friction it's going to require. So if you don't have much friction, you can't go very fast. Also, if r is large, in other words, if you have a very, very large curve, a very slow curve, so to speak, that's not very highly curved, you can go faster. The bigger r, the bigger V max. But if you have a very tight curve, in other words, what might be called a hairpin curve, if that's got a very small radius, if that's small, V max is smaller. So what does that tell you? You have to slow down when you go around a tight curve. Okay, let's stick some numbers in here and see what we got. Let's take a look at some different values here. Here I've got some different values for r, the radius of curvature of the of the curve, µs, the coefficient of static friction, and then what is Vmax given these values, which remember is root µs gr. So if r is 50 meters and µs is 0.9, there's lots of friction, we end up with Vmax is 21 meters per second. But what if it's a very icy day and there's much less friction? Even for the same radius, if µs is 0.1, substantially less than the coefficient for, say, a nice dry, sticky day between the road and the tire, say, we end up with Vmax is 7 meters per second, considerably less than Vmax for the dry day. So what does that mean? On an icy day, what do you have to do? You have to slow down. You have to drive slower to make sure you can make it around curves without skidding off. What if we go around a tight curve? So rather than 50 meters, let's say we go around a curve that's only got a curvature of 10 meters, but we'll keep µs as 0.9. What do we end up with? Vmax is 9.39 meters per second. Again, much less than the wider curve. So around tight curves, you have to slow down, even on dry days. You've got to go around slower on a tight curve. Okay, very good. Let's take a look at another rotational example where we've got a centripetal force.